Hello, I am continuing my lecture series based on Halliday, Resnik, and Walker, 9th edition, College Physics, Chapter 4, that's where we're at, we're Chapter 4, Motion in 2 and 3 dimensions. So just a quick recap, because I think it's important to look back at this for a second. In the last chapter, and the link to all of my lectures for this textbook are down below. I'll put a link to the playlist. We had the kinematic equations. So these kinematic equations define the position and velocity and acceleration time and how they relate. So we have the final position, initial position. I put this as Vx0. We just had V0 before because now we're going to deal with 2 dimensions. Ax is the acceleration in the x direction and t is the time. We also had the following. Vx was the derivative of x with respect to time, and ax was the derivative of vx with respect to time. But those are all in one dimension. After that, that was actually chapter 2. Chapter 3, we looked at this idea of, okay, well, we can express 2 dimensions or more as a vector r. And one of the ways this is the position vector r, which determines the position. We could just say r is equal to some x-coordinate in the x direction plus some y-coordinate in the y direction plus z-coordinate in the z direction. Now the book, Halliday, Resnik, and Walker writes it like this: I hat, j hat, z, k hat. I like the x, y, z better because it makes more sense. These x hat, y hat, z hats are vectors with a magnitude of 1. This points in the x direction. So this is really just the x value times the direction vector x, and the y value times the y vector. So that's how we can find the position that way. So we had a whole bunch of things. You could write also the velocity as v. I'm going to use the x hat notation. Vx x hat plus vy y hat plus vz z hat. So they have an x, y, and z component in the for velocity also. Okay, so if you remember one way, there's a couple ways to derive this equation. And it used the definition, the non-calculus way. I don't know which way you want to do it. The non-calculus way was to use the definition of average velocity. So it turns out that we can write all these definitions and all these kinematic equations as vectors also. I'm not going to rederive them because the derivation is essentially the same. But I will say that we could say V average as, instead of delta x over delta t, I'm going to say delta r over delta t. And that's equal to V 0 plus V vector over 2. So it looks the same way, except when we have vectors, we have vectors. So this would be delta r is really just r2. I'm gonna do, they use that. I'm gonna use 2 and 1. I like that better. R2 minus R1 over delta t. And let's just write this out so you can see that it's the same thing, right? If I write R2 and R1 as x1, y1, z1, x2, y2, z2, this is going to be x2 x hat plus y2 y hat plus z2 z hat. That's R2 minus x1 x hat plus y1 y hat plus z1 z hat. All of that divided by delta t. So if you remember, when we have vectors and we want to add or subtract vectors, we add or subtract the components. So if I do that, I have an x hat here and an x hat there. So it's going to be x2 minus x1. So I'm going to get x2 minus x1 x hat. And then I'm going to get y2 minus y1. So it's going to be plus y2 minus y1 y hat. And then I'm going to get the z's plus z2 minus z1 z hat. And all of that's divided by delta t. Now, if I have, this is a vector on the top, and I divide by the scalar delta t, I have to divide each component by delta t. So I can actually write this as x2 minus x1 over delta t x hat plus y2, that's a y, minus y1 over delta t, y hat, plus z2 minus z1, z hat, over delta t. And what do we have here? Well, this is going to be Vx. So it's going to be Vx is this. X hat. This is average x, right? It says delta x over delta t. This is Vy, y hat, plus Vz, z hat. And this is this, and this is that. So we actually get, if we just break it into components, I get Vx is delta x over delta t, Vy is delta y over delta t, and Vz is delta z over delta t. And so I can break it up into components. And so it is equivalently the same thing. So anything that you can do with this, you can write as vectors. So that means that these, well, not that one. That one's a little bit more difficult. These two can be written as the following vector equation. So we have the following vector equations. I'm going to start from the top. Let's rewrite V average is delta R over delta T. So you'll notice that's a vector, that's a vector, that's a scalar. So this all works. V instantaneous is going to be the derivative of r with respect to t. So how do I do a derivative of a vector? Well, let's just write this as d dt, and they're going to write r as x hat, plus y hat, plus z hat. So when I take the derivative of a vector, I have to take the derivative of each component. So this is actually just going to be dx dt x hat, plus dy dt y hat, plus dz dt z hat. So what's dx dt? Well, that's Vx x hat. What's dy dt? Why, that's Vy y hat. And what's dz dt is Vz z hat. So this is true, right? Now I have, that is V. V is Vx x hat, Vy y hat, and so forth. And then we can do the same thing for the acceleration. It's dv dt. And then we can do the two kinematic equations. I can say r final. I'll do it in the format the book uses. R0 plus v0 t plus 1/2 a t squared. So notice vector, 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 vector. Everything has to be a vector. And so t is a scalar, so I can multiply by that. My thing froze up. There it goes. Okay. And then we have the other equation, v equals v0 plus a t. Now, you can't write the final one because it deals with v0 squared, which that's not a vector. And then delta r, it depends on other things too, so it's a little bit more difficult to write that. But these two are very useful. Okay, so we still have displacement, delta r. We still have position, velocity, and I'm just looking at the summary here. The acceleration, so a would be, we could write this as ax x hat plus ay y hat plus az z hat. That's nice. Okay. Average acceleration, projectile motion. This is a big deal. Projectile motion. So this is the motion of an object with only the gravitational force. So if I take, and I'll give an example like this. Here's some ledge. And I launch a ball with an initial velocity v0. And you can put it at some angle theta. And it's going to go up and back down. Projectile motion is the motion that we have when an object has an acceleration of 0 x hat minus 9.8 meters per second squared, y hat, plus 0 z hat. So this is the x and y directions. So that's true. And something that happens, if that's true, then my kinematic equations, if I break down the kinematic equations, I'll write it this way first. I have r equals r0 plus v0 t t plus a 1/2 t squared. Now let's write this in terms of just the x components. If I just take the x components of all these out, I get x equals x0 plus, now what's the x component of the initial velocity? I can actually find that, right, from this triangle. If I know the initial velocity magnitude is v0 and it's at some angle theta, then this would be v0 cosine theta t. And then the last term is 1/2 a t squared. Well, what's a? It's 0. The x component for the acceleration is 0, so that's it. Now let's do the same thing for the y direction. In the y direction, I have y0. Now I have the y velocity, initial velocity, which is right here. That's the opposite side of that triangle, so that's going to be equal to plus v0 sine theta t. And then I'm going to have the accelerations negative 9.8. We call that, we say g is 9.8 meters per second squared. So it's going to be minus 1/2 g t squared. So you get these two equations, one for the x direction and one for the y. And this is the key right there to projectile motion. The other key is this. Because this motion up here has no y's in it, and this one has no x's in it, then the t here has to be the same as the t here. So when you have a motion, you can break this into a one-dimensional x motion of an object moving at a constant speed, a one-dimensional y motion of an object going up and down, and those two motions take the same time. So the trick is to solve, almost always solve this one for time, and then use that up there to solve for position. Now, you be careful. If I have an initial y velocity, this is going to have a t and a t squared term in it, so you might have to use a quadratic equation to solve for time. And you'll get 2 times, and if I launch this up here like this, I'd get 2 times. One would be positive, the time it takes to get over here, and one would be negative. So if you went back in time to when y was equal to 0, it'd get over there. There's a whole bunch of stuff to projectile motion, but this is a chapter summary, really. If you need lots of problems, you can do that. Okay, I'm looking right here. They have the trajectory equation. I think that's a little complicated for introductory physics. I wouldn't worry about that. The range equation, I think, is a terrible, terrible, terrible equation. You'll see it, though. R equals v0 squared over g times sine of 2 theta. This is the range equation. Be very careful. One, you can derive this up here. If you take this situation and you start with some velocity at some angle at y equals 0 and you end at y equals 0, you get this. Now there is a double angle formula that you have to use to get this, but it's not a big deal. But this only works if you start and end at the same location. If you start higher up and end lower down, this doesn't work. If you start low and end high, that doesn't work. Okay, so I really don't think that is a big deal. Okay, this one is a big deal. Uniform circular motion. So suppose I have an object moving in a circle. That's a pretty good circle right there. So uniform circular motion means that we have some object moving with a constant magnitude velocity in some circle of radius r. Now, if you look at the definition of acceleration, it's dv dt. Now, if the magnitude is constant, it doesn't mean that the derivative is 0, because in fact, as you see this one, when it's over here, it'll be going down. So the x and y components of this is the x direction, and this is the y, do change. So even though it's moving with a constant speed, it does have an acceleration. And I'll go ahead and tell you the answer because that's the important part. The acceleration is the magnitude, I'll write it as a magnitude, is v squared over r. The direction of this acceleration, I'll put it over here because I'm going to use that picture in a second. If that's v, the direction of the acceleration is towards the center of the circle. And that's why this is called centripetal acceleration. Tripetal acceleration. This literally means center pointing. Center pointing acceleration. Don't confuse that with this centrifugal acceleration, or force, either way is fine. Acceleration, it's hard to spell when you're on YouTube. This is center fleeing. So this is the force that pushes away from the center of the circle. This is actually what we call a fictitious force. It's not normally used in introductory physics courses. I just want to tell you because I think you're grown up and you can handle it. Or a teenager, whatever you are, I think you can handle it. If you're in this course, you can handle it. This is a fake force. So what this does is, if I want to assume my frame of reference is accelerating, I need to add this force to make physics work again. So we tend to use this centripetal acceleration in physics just because it causes fewer problems. Okay, so let's see if we can derive this value right here. So I'm going to say that I have this r and theta. Okay, so the object is at some position theta, and the radius of the circle is r, and that's a constant magnitude velocity. So let's see if we can write the velocity as a vector. Well, let me take this blue marker right here. I need the x and y components. Well, if I draw this, actually I don't need that one. I want, here is my y, and here's my x, right? So it's going that much at this instant, it's going that way in the y direction and that way in the x direction. And you'll notice that this angle theta is the same as that. So just imagine that this whole thing went back down to here, then that angle theta would go to 0, that angle theta would go to 0. So I can write this as the following vector. So the x component is going to be the magnitude of the velocity, v, but it's in the negative x direction, right? It's moving this way. So it's going to be negative v. And then I'm going to say sine theta x hat, because that's the opposite side of this right triangle. And then the x component, the y component is going to be v cosine theta y hat. So that's my vector, acceleration vector. I can get sine and cosine of theta by looking at this triangle. Since that's the same triangle, I'm going to write this theta r x y. So if this triangle right here has the same angle, remember sine is just a ratio of sides. This has the same, as a right triangle with the same angle, it has to have the same ratio of sides. So if I take the sine of theta right here, I could take the sine of theta down here. And sine of theta, I'll write it right here, is equal to opposite of hypotenuse. That's going to be equal to y over r. And then cosine theta is going to be adjacent over hypotenuse. That's going to be x over r. So I can put those in up here instead of sine and cosine, and I get the velocity is equal to negative v over r y x hat plus v over r x y hat. But now and this is a constant, right? So I can actually, v and r are constant. V is the magnitude of the velocity. We said it's moving at a constant velocity. So this is going to be equal to v over r times negative y x hat plus x y hat. Just a note, if this derivation is like blowing your mind, it's fine. I don't normally see students having to use this. Just as long as you know this is true, you don't always have to derive it. But now I know the expression for the velocity, I can derive an expression for the acceleration. So let's just recopy that down because it's important. So I'm going to say v equals, v over r negative y x hat plus x y hat. Now I'm going to take the derivative. I'm going to say the acceleration is dv dt. And what is constant and what is not? Well, v is constant and r is constant. It's the same size circle. It's moving at the same speed. So that's a constant. So when I take the derivative, I just have to take the derivative of the stuff inside of here. So this is going to be, let's write it out. V over r negative dy dt x hat plus dx dt y hat. Well, what is dx dt? That's the x velocity. That's the y velocity, I'm sorry. And that's the x velocity. So this is actually going to be equal to v over r negative vx, no vy, x hat, plus vx, y hat. And that's a vector. But I want to find the magnitude of this vector. A magnitude is going to be, I could break this into two pieces, but I'll just do it all in one time. I can factor out that. All I need to do is find the magnitude of this part, right? Because that's just a scalar anyway. So this is going to be equal to v over r times the square root of the x component, which is going to be vy squared, plus the square root of the x component, which is the y component, which is vx squared. But if you see right here, I have vy squared plus vx squared square rooted. That's just the magnitude of the velocity v. So this is going to be v over r times v, or v squared over r. Okay, so now we need to get the direction of this vector. So let's go ahead and go back a second to this definition of velocity. So I'm going to write this. V equals negative v sine theta x hat plus v cosine theta y hat. So if I put that in up here, I can say A equals v over r. I'm going to factor out the v. So v squared over r times negative sine theta x hat plus cosine theta y hat. And this is what we would say, this is a unit vector. Actually, that's not right. I did something wrong. Let me see. I've wrote it on the board over here. Wait 1 second. So this is, maybe I should just write this as, okay. So then if I draw this, so I'm right here, theta, I'm right there. What direction is the acceleration? Well, it's going to be negative sine theta. So sine theta is this side. So it's going to be down. No, it's going to be back and up. Okay, I'm not going to worry about the direction. I messed up on the direction. That's fine. I'm cool with that. Hope you're cool with that. I had it and I just forgot how to, I don't want to make it all messy and stuff like that. Okay, now there is one other thing in here that I don't think is, well, it's kind of a big deal. And that's relative velocity. So imagine that there is a car, a train car. And it's moving with a velocity v train with respect to the ground. And now I have a person inside there that's moving this way with the velocity of the person with respect to the train. And then I have a person over here. And they want to see that person moving because there's a window in this for some reason. I can say the following. The velocity of the person with respect to the ground is equal to the velocity of the person with respect to the train plus the velocity of the train with respect to the ground. And this is your relative velocity formula. So one of the key things here is always to use a notation of the object with respect to the reference frame. Object, reference frame, object, reference frame. And then if you line these up so these two match in your equation, then you get these two. I know it's kind of stupid, but that is true. And you can see that it makes sense here, right? If this is moving at 10 meters per second and the person's moving at 5 meters per second, then this would be, we can actually write it out. Velocity of the plane with respect to the train is 10 x hat meters per second. Velocity of the person with respect to the train with respect to the ground, I'm sorry, that's this one. VTG, VPT is equal to 5 x hat meters per second. And then if I add those two together, I get 15 meters per second in x direction. So it works. But here's the awesome thing. It doesn't even have to be lined up, right? So if I have a river like this is a common one. Here's a river flowing with velocity of the water with respect to the ground. And then I have a boat that aims directly across, velocity of the boat with respect to the water. Then I can get the velocity of the boat with respect to the ground. Velocity of the boat, ground, is velocity of the boat with respect to the water, plus the velocity of the water with respect to the ground. And if you write these as vectors, as a vector equation, everything will work, and it works out just fine. So it's not too bad. Okay, so that's it for chapter 4. And just a quick reminder, there is a lot of stuff here. Okay, and I fly through this. What you need to do is you need to read through the chapter, study the stuff, practice problems, work through the practice problems, do the homework. Don't feel like you can just watch this YouTube video and get it. There are maybe some people that can do that, but that's not how most people learn. You have to really, just seeing it is not just getting it. Okay, so make sure you work on that. If you have questions, post the questions down below. I'll try to answer them if I can. So hope that helps, and I'll see you in the next chapter.